Good morning, good afternoon, and good evening or good night, wherever you're joining us from. It's a pleasure to be here with all of you. And we thank you for joining us so that we can talk about an exciting topic, which is improving locomotive starting performance. So this will be a comprehensive review on the application of supercapacitor starting technology, assist technology, the impact it has on locomotive starting performance, and the impact it also has on some other key goals for railroads. The rail industry plays a crucial role in transportation, with a strong emphasis on efficiency, cost reduction, and more recently, environmental sustainability, with goals in that regard spanning out to 2030 to 2040 and to 2050. With this focus on improving operational performance, reducing the carbon footprint, the rail industry is continually looking for technical solutions to improve locomotive efficiency, reduce their operating expenditures, and increase environmental sustainability. This has led to the proliferation of technologies, some of them that are quite new and exciting to achieve the above goals. But in some cases, these technologies have had an inadvertent, undesired impact on locomotive availability, fuel consumption, and emissions. And it all starts with batteries. So lead acid batteries, it's a well-proven technology that has evolved over decades, used in numerous industries, and when in the right application has proven to be robust and a great solution for starting engines, whether it be in locomotives, diesel applications, gas engines, the automotive industry, trucking industry, and the like. Indeed, decades ago, battery health wasn't a problem, and lead acid batteries were used solely for starting purposes on locomotives, which is exactly what their intended application is. Long time ago, decades ago, basically locomotive engines ran a long time, so charging was more than sufficient. Starting and stopping of the engines was infrequent because they had long idle times. There wasn't much regard for fuel reduction and fuel savings. And there were virtually no hotel loads or electronics to power. Maybe some lighting and cab lighting, but that's about it. However, battery utilization changed over the decades. And again, going back to the pre-1980s, no problems there. However, in the 1980s, fuel prices started to rise. There was some adoption of shutdown policies to conserve fuel and the introduction of computer control systems. The 1990s saw increased legislative requirements to reduce emissions and the introduction of automatic engine stop-start systems to save fuel. These systems are also known as AESS, which will be referred to throughout this presentation. The adoption rates for this technology climbed, and also increased loads on the battery when the engine is shut down. In the 2000s, this trend continued with more computer monitoring systems such as PTC and other cab electronics. Now today, this proven battery technology now underperforms. Charging is inadequate because the engines don't run as long as they used to. The stop-start frequency is high. And the hotel loads, another way of saying the loads when the engine is powered off, they're much higher these days, and then the battery should be subjected to when the engine is shut down. Starting lead acid batteries like to be fully charged most of the time, and only discharge for a small period of time during the engine crank cycle. So this cycle they're now in today, a frequent stop-start, partial charge, and long shutdowns with hotel loads, has reduced, can lead to some things like permanent sulfation on the plates, reduced capacity, performance, and impacting the lifespan of these batteries. This impact on the batteries has a cascading effect. First, the inability to discharge energy at high rate leads to failed engine starts, which results in operational disruptions and the impact on locomotive availability. There's also reduced effectiveness of the AESS because of this. Most AESS systems need to keep the engine running until certain parameters are satisfied, one of which is the state of battery charge. So batteries in poor condition may need to charge longer, which leads to excess idle times, which impacts the performance of the AESS and ultimately the fuel reduction goals. In addition to that, most AESS systems restart when the battery voltage dips to a certain level. And batteries in a poor state of health will hit this threshold, often decreasing engine shutdown time because the AESS has to trigger a restart. This reduced fuel savings, of course, directly impacts the decarbonization goals. Having outlined these challenges the batteries face and the cascaded effect from them, the solution here is supercapacitor starting assist technologies, which are an excellent means by which to address these issues and which make financial sense, which we're going to talk about a little bit later. We will outline how this technology can help avoid dead won't start incidents and sometimes you'll see it shown as DWS, which means the engine couldn't start because of a battery related issue. This technology will also reduce unscheduled maintenance on battery and starting systems when there's a failure, reduce emissions, and provide financial returns that are attractive, and again, which will be outlined later. On these upcoming slides, we'll show analysis based on data collected from the ZTR KickStart supercapacitor solution technology, which has been installed on thousands of locomotives globally. And we'll demonstrate how this technology can improve locomotive availability, reduce fuel consumption, lower emissions, and all the while provide an attractive return on investment. Utilizing supercapacitors, which are a high-power energy storage device, they can provide the instantaneous power required, or the torque, to get that massive diesel engine turning. To get a 4,400 horsepower engine turning at sub-freezing temperatures, like say 20 Fahrenheit, requires high current that the battery in certain conditions may not be able to provide. This technology we're talking about here provides a reliable engine starting and offloading of the batteries. So I'll explain a little bit about the difference between supercapacitors and lead-acid batteries. Here we have a graph with the energy density on the y-axis and the power density on the x-axis. Lead-acid batteries are the clear winner when it comes to the energy density. Some of them can contain over 130 million usable joules of energy, which translates to this higher energy density. However, they cannot deliver that power at a high rate, which means a lower power density. On the other hand, supercapacitors may only contain 1,000 usable joules of energy, as an example, translating to a low energy density. However, they can provide that energy at a very high rate or a high power level. And this is where supercapacitors have that advantage, which is required to get that engine turning. The next few slides will outline at a high level how the supercapacitor starting assist works. So here in this diagram, the locomotive engine in this state is running, and the auxiliary generator on the locomotive is charging the batteries, and it's also charging the supercapacitor system. Now the engine is off, and the supercapacitor is isolated from the battery system and maintains its charge. And as in the case of KickStart, there's isolating contactors inside the capacitor module to make sure that the supercapacitor is disconnected from the battery system during the engine shutdown. Now the engine is about to crank, and just at the beginning of the crank cycle, the supercapacitor connects with the battery to the starting circuit, providing the peak current to successfully turn the engine, and then working with the battery provides the energy for the rest of the successful engine crank. This process then repeats itself over and over again. So improving locomotive availability. These graphs show an engine starting sequence with and without the supercapacitor and the impact on the battery voltage. In the diagram on the left, without the supercapacitor assist, this is a very depleted battery. And as you can see, when the engine goes to crank, the battery voltage dips significantly well below 50 volts. And in this case, closer to 10 or 20 volts, it was a particularly poor battery. And because of that, the onboard computers, some of them recycled and rebooted, which can result in operational delays. And in this case, obviously, the engine did not turn over successfully. In the graph on the right, there's a supercapacitor assisting. In addition to providing the peak torque or the current to get the engine turning, another benefit is that the resulting engine rotating velocity is maintained higher, which means less of a voltage drop, which means computers will not reboot and no operational delays. So continuing with talking about improving locomotive availability, we've seen how KickStart operates and how it improves starting reliability, which in turn means improving locomotive availability. Statistics have shown that locomotives will have a dead won't start occurrence once every 3 years on every locomotive, meaning this was a failed start because of batteries. This is avoidable with the implementation of supercapacitor starting assist technologies. When it comes to the financial impact of the dead won't start, the numbers can be startling. These costs can range anywhere from $4,000 to mainline locomotives, maybe up to $45,000. And we've heard numbers as high as $1 million. It really depends on the operation, the penalties for late deliveries, how many locomotives were taken out of service. Are you impacting and are you operating on a transit line and you're delaying transit trains? So these numbers can really add up. So if we go and assume an average cost of $21,000 per dead won't start, avoiding one of these every 3 years across a fleet of 1,000 locomotives could save a railway over $7 million each year across those 1,000 locomotives fleets, simply by improving the starting reliability through use of a supercapacitor system. Another benefit is the impact on battery life. Locomotive lead-acid batteries can prematurely fail due to internal corrosion, sulfation, and loss of electrolyte. These battery failure mechanisms are accelerated by deeper and more frequent discharges, as well as battery temperatures. Recall that lead-acid batteries like to be fully charged most of the time. The batteries today are in this permanent state of deficit charge, which accelerates some of these failure modes. With the implementation of supercapacitors to assist the start, the useful life of batteries are extended. And I'll explain what I mean by useful life. As an example, consider a battery in a poor state of health that is unable to provide power and peak current required to turn the engine. In many cases, this battery would simply be discarded. However, this battery, complemented by a supercapacitor system, can extend its useful life, meaning working with the capacitor, it can start the engine and then work to provide power to the loads when the engine is off. The typical battery life of a lead-acid battery, we've seen some statistics in applications with AESS expected to be as low as 2 years. This life can be doubled by going to an expected 4 to 5 years by installing a supercapacitor starting a system. Given a typical battery replacement costs about $6,000 per locomotive, and by the way, when I get into the numbers, the dollar is in US currency, just to be clear with what the numbers are. So we go with $6,000, the supercapacitor system can save about $6,000 to $12,000 in battery replacements over 5 years on each locomotive. Continuing on with the data from our case studies, we have seen a reduction in engine crank time with the assistance of a supercapacitor system. More studies will be conducted, but this should suggest an increase in the lifespan of starting equipment, such as starting motors and batteries, because they're not subjected to the crank cycle as long as they were previously, and also shows the effectiveness of the supercapacitor system during a start. So having discussed improving the starting reliability, now we'll talk about some other benefits that come along with the supercapacitor system, namely reducing locomotive fuel consumption, which is a critical driver of locomotive operating expense. It is the second highest expense for a railway, and while idling can consume 4 to 5 US gallons per hour and up to 200 gallons per hour for larger locomotives when in operation, and it can cost, if you project that, about $800 and sometimes $800 in fuel per hour of operation. Just going to pause for a second here. We previously outlined AESS operation And the system will idle and not shut down until certain parameters are satisfied. When I say shut down, I mean shut down the engine until certain parameters are satisfied for operational equipment protection and safety reasons. This diagram from our study on a switchyard locomotives showing a breakdown of the parameters the ASS is waiting on. This study is over a period of time before the engine shuts down. As with many locomotives, we typically see main reservoir or brake cylinder pressure charging as one of the reasons the system will idle until these are satisfied. And here it's shown to take about 50% of the idle time of the ASS. We also see in this study that about 20% of that idle time is due to battery charging. If we take that 20% and dive into it, what we found in this study with the supercapacitor system, the offloading of the batteries during the engine crank cycle, over time, we saw a slight amp-hour power reduction from the batteries, which resulted in reducing the time it took to charge the batteries when the locomotive was idling. So that 20% we reduced by 50%, which went down to 10%. So that meant a 10% overall reduction in idle time before the engine can shut down. And in this study, we saw an average of the 36 hours per locomotive per month waiting for batteries to charge after the supercapacitor system was installed on a group of locomotives. That 36 on average went down to 18 hours per month. That's where that 50% reduction comes from. We also noted earlier that the ASS system will restart due to certain parameters, and one of them is if the battery voltage drops too low. In our study on that group of locomotives, we saw an 85% reduction in the occurrences of battery-related ASS restarts, which means the locomotive is starting less often for batteries, which extends its engine shutdown time and reduces fuel consumption. From this study, we saw approximately 1,080 gallons per locomotive per year being saved. And assuming $4 a gallon, this comes out to $4,320 in annual fuel savings per each locomotive. With this noted fuel reduction of 1,080 gallons per locomotive per year, this results in reducing locomotive emissions and taking the railroad steps closer to reaching decarbonization goals. So put another way, that 1,000 gallons per year equates to approximately 11 tons of CO2 per locomotive per year reduced. If you project that across a fleet of 1,000 locomotives, doing the math, means almost 11,000 tons of CO2 reduced each year. And if you go according to the EPA, that means taking 2,219 cars off the road and increasing forest space by about 12,000 acres. Breaking that down further, here's what it means in reduction in air quality contaminants. So over 7,000 grams of particulate matter, close to 29,000 grams of carbon monoxide, and approximately 150,000 grams of nitrogen oxide, all reduced over 1,000 locomotives per year. So having talked about fuel savings and emission reductions, this next section of the presentation will focus on the upfront costs and then the financial returns. For these calculations, we will assume the cost to get up and running will be about $15,000 or less, like a KickStart type product, which is quite low in comparison to the overall value generated from the system, which we'll talk about here shortly. The supercapacitor systems are typically maintenance-free and can withstand hundreds of thousands of charge and discharge cycles without degradation in different climates, making them much more durable than traditional batteries and without any ongoing maintenance costs. Here we take a look at the return on investment after 1 year, which is important to understand when implementing this technology. In this analysis, we're looking at the annual savings per locomotive taking into consideration fuel savings, reduced maintenance costs, and improved operational efficiency. So if we take the numbers we previously outlined, such as $4,320 in annual fuel savings, $6,000 per year in avoided cost in preventing failed engine starts. So this is improving starting reliability and not having operational disruptions, mainline failures because of a failed start. And then $3,000 per year cost avoided by extending battery life and not having to change them out. So taking all these numbers in, the total annual savings are projected per locomotive with this type of supercapacitor solution to be about $13,000 to $14,000 per year. This results in breaking even after approximately 1 year of use. Taking a look long-term at this, the supercapacitor systems, they do benefit from durability and longevity. Being maintenance-free, this helps ensure long-term savings over, in this case, a study of 10 years, resulting in favorable payback. So you can see that after the first year, and then the 5-year return being just under $50,000, and then the 10-year return being $112,000, which should be considered against a relatively low upfront investment of $15,000, which we previously outlined. So in conclusion, and in summary, the application of supercapacitor starting assist technology on locomotives can provide significant benefits to the rail industry. This comprehensive review has shown that installing a system like the ZTR KickStart supercapacitor technology can help improve locomotive availability, reduce fuel consumption, and lower emissions. With fuel consumption being a significant driver of locomotive expenses, any reduction can substantially impact profitability. Supercapacitor technology also plays a crucial role in reducing locomotive emissions, which is essential for meeting decarbonization targets. Furthermore, by improving locomotive availability and reducing operational disruptions, the railroad can enjoy increased metrics related to on-time departure and delivery for their end customers. After all, they have their customers too, and moving our economy forward. Ultimately, the findings show that implementing supercapacitor starting assist technologies can be an excellent solution for railway companies to improve efficiency, reduce operating costs, and increase environmental sustainability with attractive returns. Thank you. That concludes the presentation. And James, I will turn it back to you.
Thanks, Am. Now, there may have been a little bit of an issue for some people with the Q&A function. Due to that, I have turned on the chat function. So if you do want to submit any questions, feel free to do so using the chat option. We did have some questions come in prior to the webinar during the registration process, so I can field or send some of those to you, Am. One of the questions here was, what are other industries that supercapacitors are used in?
Yeah, so supercapacitors, they're commonly used in electric vehicles for regenerative braking and those types of applications. They're also been used significantly in the trucking industry, because the trucking industry with their diesel engines also suffered from poor starting performance with the introduction of with start-stop systems. So supercapacitors, we have a precedence in the trucking industry where they've been used for a long time as a starting assist technology as well.
All right, thanks, Am. Another question here. How long does it take to install, and is it hard?
So, yeah, so in our experience, it's not hard. Being biased with our own product, we typically provide a lot of detailed information that goes with it, but it usually involves the installation of a capacitor panel, connection to the batteries, possibly a control panel, maybe some disconnect switches, and some connections to the locomotive, to the starting circuit, just to be aware of the locomotives being started. And in our experience, it typically, once a customer is up to speed, can be typically done in about, say, 2 shifts with 2 people.
Perfect. Couple questions coming in here. Which kind of EMD locomotives can you install supercapacitors on?
Yeah, good question. So some EMD locomotives today do have air start systems, so obviously they may not be quite as applicable, but pretty much any EMD type locomotive going back from the switchyard locomotives to the SD40s to the modernized locomotives today like SD70s, as long as they're using batteries to start the engine, KickStart is applicable to those. And they're actually applicable to pretty much any locomotive, EMD type, with the other OEMs. And we've got them installed on those types of locomotives across the different models globally.
Perfect. Another question here. And we didn't have a diagram, but how big is a KickStart?
So the capacitor module, I have to think about this and do a little bit of this. I'm going to say it's probably maybe 18 inches by 18 inches, the panel. Lucas, does that sound about right to you?
Good question. Yeah, that sounds about right.
Thank you.
All right, Am, another question here. What's the lifespan of the capacitors?
So we ask our vendors that question, and when we work with our technology partners, they look at our application, they look at the temperature ranges, and there's a number of factors that can affect the lifespan of supercapacitors. Temperature and voltage are the key items. With our system, what we do is we keep the capacitors are rated for the locomotive environment, like -40 to 70. And we also, I may have mentioned earlier in the presentation that we have isolating contactors and switches inside our solution to isolate the capacitor at times. One of the benefits of that is if we see a higher voltage than what the capacitor should be subjected to, we can isolate and protect them. So we're thinking probably 10 to 20 years.
All right, I have another question here that was asked prior to the webinar. Is there any maintenance for the KickStart itself?
No, it's maintenance free and transparent to the crew as well once it's installed. So what I mean by that is when the operating crew gets on locomotive to run the train, they do what they normally do: isolation, switch and run, turn breakers on, that type of thing, and they don't have to do anything related to KickStart itself.
Is this sorry, I have another question here. Is this in connection, or is it connected to the cranking circuit in parallel or separate circuits for lesser time of cranking?
It's connected in parallel with the battery. But again, it can deliver the current to the starting circuit much faster than the battery can.
What's the typical cost of the system?
So we the price for the system should be, I think I outlined some numbers earlier, about 15,000 or less, but it depends on the quantity and that type of thing. But happy to, if someone wants to reach out to ZTR sales, James, I don't know if you have the email or the website available right now that they can reach out and get a more detailed quote.
Yeah, of course. Obviously, anyone can reach us at ZTR.com. It's our website. And then if you go to ZTR.com/contact, we'll feel free to ask any questions, maybe a little more technical in nature at that point, and we'll be able to get back to you. We also will be sending out a white paper and a copy of this webinar to registered users. So we can send along schematics or any diagrams of the product itself as well. Now, just want to ask another question here. How long can the capacitors hold the charge before it starts to drain voltage?
So it's a good question. I should have that number off the top of my head, but I don't. But typically in the operation where we're seeing them, it's the discharge rate is not a concern because they're typically coupled with AESS systems, and most AESS systems have to restart, fairly frequently, like within 1 hour to 4 hours. And in that short time frame, the discharge of the capacitor is negligible on the performance. And we've seen supercapacitors after, week or 2 weeks and that type of thing, where they're still have enough energy stored to provide a successful crank.
I know we asked a question about EMD locomotives, but we have one here. What types of locomotives does it work on?
What types of locomotives?
Yes.
So, yeah, so broadly speaking, any type of diesel electric locomotive that uses batteries and an electric starting circuit, it's, as examples, pretty much every EMD locomotive we've come across, KickStart can operate on it. And we have applications on, like I said, switchyard locomotives, SD40s, mainline SD70 type locomotives. Doesn't matter if it's AC, DC traction, it's all about the starting circuit. We have KickStart installed on several Wabtec type locomotives as well, Dash 9s, AC 4400s, the ES series of locomotives. So, and then, in the markets outside of North America, we've got them installed on, narrow gauge type locomotives, GT locomotives, GEU style locomotives. So again, it's really agnostic to the locomotive model. It's just, does it have a battery and does it have electric starting circuit? It can be installed and it can assist.
Sam, well, we have had a couple of questions come in on fuel consumption. Would it be possible, Ham, for you just to go back and maybe go over a little bit of how supercapacitors themselves save fuel, like the correlation between the two?
Yeah, sure. So when coupled with an automatic engine stop-start system, the automatic engine stop-start system has to idle and it can't shut down until certain parameters are deemed to be at a certain level, whether it be for safety. So for example, the brake systems, the brake pressure system has to be at a certain point. The ambient temperature in some cases has to be at a certain level. Most diesel locomotives are water cooled. So the engine water temperature has to be at a certain level before it can shut down to reduce the risk of a failed start, or in the worst possible case, freezing of the engine block because it's water cooled. So it looks for these, but it also looks at the state of batteries. It wants to make sure the batteries are charged to a certain level before it shuts the locomotive down so that it knows it can theoretically restart the locomotive. When KickStart is involved, it actually takes a little bit, shaves some of the amp hours off of the battery during the crank cycle. And what we've seen after a period of time is that it takes enough of amp hours from the battery, and it actually saves the amp hour throughput of the battery. And that means the charge time is slightly reduced. And it's not by a lot, we're talking some amp hours, but lead acid batteries, when they're close to being charged, that's when it doesn't take lead acid batteries a long time to charge from, say, 40% to 70%. It takes a long time to charge from, say, 90% to 95%, that tail where the slope really drops off. And this is where the AESS is sitting there twiddling its thumbs, waiting for it to drop just a few more amps, a few more amp hours, or a few more percent to charge. And again, so that little amp hour reduction that KickStart's helping with, it saves a lot of time where the AESS is idling, waiting for the system to start. So that's where the fuel savings come in. I hope that answered the question. Bit of a long explanation from me.
Thanks, Sam. We got another question here. I think what they're looking for is confirmation as to whether or not this will work on gen start locomotives where there are no starter motors present.
Yeah, so if we're talking about gen start locomotives, there's a few that I hope I understand we're referencing here. The first types are the ones that were the old switchyard EMD locomotives, where they used like DC generators that had a start winding inside them. I'm going to say, I hope I'm not wrong on this, like D25, D32 type generators. There may be some older GE locomotives that have that as well. So KickStart is applicable. And even on the newer locomotives that have traction alternator start, where the battery is converted to AC powered, and basically the traction alternator turns into a synchronous motor to start the engine. KickStart is applicable there too. And as I mentioned, we have well over 1,000 at least, I think, on those types of locomotives.
Okay, Em. I think we're pretty much wrapping up right now. I want to thank you for your time and answering all these questions. Any other questions that might come in, or if people do have other questions or things they haven't asked yet, but like I said, we will be offering a white paper on improving starting performance for locomotives, as well as a copy of this webinar. You can access it, or anyone registered will get it emailed to them, but you can also access it at our website at www.ztr.com.